Welcome to Math with Professor V. In this video, we're going to go over how to test an infinite series for absolute and conditional convergence. Now, I just want to get a couple definitions out of the way, and then I'm going to give you an analogy to help you understand what exactly is going on, because students really struggle with this topic. So if you're in that boat, don't feel bad. You're not alone. Okay, absolute convergence is when you take the absolute value of the terms of your series and it converges. Okay, so we say the original series converges absolutely if the sum of the absolute value of the terms converges. Okay, great. Now, conditional convergence is when the original series converges, but not absolutely. So that means if you take the absolute value of the terms, then it would diverge. But as is, the OG series, it will converge. Now, the strongest kind of convergence is absolute convergence. This guarantees that you have conditional. So absolute convergence means that the absolute value of the terms, that sum converges and the OG converges. Conditional means absolute value diverges and the OG converges. And it's just a lot of terms, a lot of mishmash in the head. So I'm going to break it down. I want you to pretend you're an admissions officer at a university for their math department. Yes, you're reading applications from students who want to be math majors, because who doesn't want to be a math major? So you need to answer two questions when you're looking at the applications to decide who you're going to admit. The one question you need to answer is, does the student who's applying have a 4.0 GPA? And then the other question you need to answer is, does the student have an A in their most recent math class? Now, think about it this way. In order to answer both these questions, there's one that you should always check for first to do the least amount of work possible. If you know that the student has a 4.0 GPA, then you are done. You have the answer to the second question. You know that they also had an A in their most recent math class. And that's akin to testing for absolute convergence. So if I test for absolute convergence and the answer is yes, then I am done. I know that my series converges absolutely, which is the strongest type of convergence, and therefore, of course, it converges conditionally. I don't need to do any other work. But say you check their transcripts and you're like, oh yeah, they had an A in their most recent math class. Have you answered whether or not they have a 4.0 GPA overall? No, you still have to go back and check that. So that's what happens when you check for conditional convergence before you check for absolute. Sometimes it creates more work for you. Here's the other thing that's super helpful that I've been trying to remind my students. When you test for absolute convergence, you take the absolute value of the terms, right? And you can use any test except AST, alternating series test. When you test for conditional convergence, guess what? You only use AST. Okay? So, if you're using AST, that will only tell you about conditional convergence. If you're trying to determine absolute convergence, which you should pretty much do first, always, we'll talk about a couple cases where you don't need to, then you can use any test that you have except AST. So let's think about the test. We've got integral test, comparison, limit comparison, and then we get to the magic two tests, ratio and root tests. So ratio and root tests are special because they're all or nothing tests. Okay, so ratio and root, they will tell you if a series is either absolutely convergent or divergent. There's no in between with ratio and root test. Okay, so those are two special ones. Just remember that. So I have a full flowchart for you. Everybody loves a flowchart. I've shown this before. Let me scroll out if you want to take a screenshot, but it's also up on my Patreon if you want to download it there. Okay, so you can pretty much follow this while you're testing for absolute or conditional convergence. Test for absolute convergence first. This is like determining the answer to the question, does the student have a 4.0? If it's yes, then you're done. You can say the sum of AN converges absolutely. If it's a no, then you have to check, does the series converge conditionally? Meaning, does the student have an A in math? That's the second question you'd have to get answered. You always will use AST to check for conditional convergence. If you get yes, you're done. You say your series converges conditionally. If AST fails, then you still need to show that the sum of AN diverges using the test for divergence. Sometimes, okay, there are exceptions to this little flowchart. If you can spot that this is going to happen, you can just detour straight here. I'll do an example where I do that for you, okay? And then, like I said, if you get a no using the ratio or root test, then you're done. You don't do AST to check for conditional convergence. Ratio and root are all or nothing tests. Either it converges absolutely or it diverges when you use those tests, okay? Again, when you're testing for absolute convergence, you can use any test except which one? Very good, AST. AST is only for conditional convergence, okay? You guys, let's jump right in. I have some examples that we did in class, and I'm going to work through them again with you guys here. Okay, determine if the series converges. Absolutely converges. When it says just straight up converges like this, it's conditionally, okay? Or if it diverges. Okay, what should I test for first? I want to test for absolute convergence first, okay? So in order to do that, I have to take the absolute value of AN. What happens when I take the absolute value of AN? This alternating portion goes away. So I'm just going to have 1 over square root of n squared plus 1 plus n. Okay, anytime you have something, it's not a rational function technically because these are not polynomials, but when it kind of looks like a rational function, I'm thinking limit comparison and I want to pick a p series. Do you know what I mean? So let's see, what would be the appropriate p series to compare this to? Look at the highest power of n in the denominator, which is actually, very good, n to the first. Because I have n to the first here, and this n squared is underneath the square root sign. So it's only really growing as fast as n to the first. So I'm going to let bn equal 1 over n. And then don't forget this part. This is important. The sum, n equals 1 to infinity of 1 over n, you have to state that you know what it does, diverges because it's the harmonic series. Make sure you don't forget to write this sigma here. Otherwise, it's not a series. This is just a sequence, and it's actually a convergent sequence, but as an infinite series, this is a divergent series. So make sure you include that every time for your justification with limit comparison. Okay, so here we go. It's time for limit comparison test. Let's tell the people that's what's happening. I'm going to take the limit as n goes to infinity of 1 over the square root of n squared plus 1 plus n over 1 over n, which is going to be the limit, n goes to infinity. 1 over n is going to flip up to the numerator, so I'll have n over square root n squared plus 1 plus n. Okay, now what do we do? Well, I have numerators going to infinity, denominators going to infinity. No, we're not doing L'Hopital's rule. We'd have to change it to a function of x because these terms are not differentiable. Plus, that's overkill. All we need to do is divide everybody by n. Same as multiplying by 1 over n. Highest power of n from the denominator always. Okay, limit n goes to infinity. I'm going to have a 1 in the numerator. Now be careful. When you divide or when you're multiplying by 1 over n and it comes underneath the radical, it's going to become n squared, n squared. So underneath the radical now, I'm going to have 1 plus 1 over n squared and then a plus 1. How are we doing? We're great, Professor V. Okay, perfect. So then from here, let's see, 1 over n squared, this is going to go to 0. Then I have 1 over square root of 1 plus 1, which is a half. What do I care about this limit? When you do limit comparison test, you need this limit to be finite and non-zero, which it is. Woohoo! So what does that tell me? That tells me that my series, which was the sum n equals 1 to infinity of 1 over square root n squared plus 1 plus n, and the harmonic series behave the same. They're twinsies. So since the harmonic series diverges, that tells me my series also diverges by limit comparison test. Was this the original series? No. This is the absolute value of the original series. So what do I know about the original series, which had that alternating component in the numerator? The sum -1 to infinity of -1 to the n over the square root of n squared plus 1 plus n. What do I know about that? It does not converge absolutely. Okay, so what did we just determine? Let's think back to our analogy. The absolute value of the terms diverged. So we checked for the strongest type of convergence. We don't have it. So this student does not have a 4.0. Are you going to reject them as a math major from your department, from your program? Well, no, maybe they don't have a 4.0 because of, some Pilates class they took. Let's check. Did they get an A in their last math class? So I want to check now for conditional convergence. What test do I use for conditional convergence? There's only one. That's right, AST. So we're going to check for conditional convergence using AST. Always and forever. Students love a good always statement. Here is one. We can't always give them to you, but here's one. Okay, for AST, you need to identify Bn, which is the same as absolute value of An. So it's 1 over square root n squared plus 1 plus n. Okay, so I have to check two things. First, is Bn decreasing? Let's see if we could just use the definition and not have to take a derivative. Bn plus 1 would be 1 over square root n plus 1 squared plus 1 plus n plus 1. Oh, only the denominator is changing, right? Do you see that? In Bn plus 1 compared to Bn, this is Bn. So the denominator got larger. Numerator is the same. Therefore, if the denominator is larger, this has to be smaller. This is the definition of decreasing, to say the following term, Bn plus 1, is smaller than the one that preceded it. Okay, so for sure we passed that. And then the second thing, I want to make sure the limit as n goes to infinity of Bn is 0. Oh, this is a nice, relaxing little limit. Look at that. The denominator is clearly going to infinity. So I have 1 over something getting very, very large. This is going to be 0. Very good. So both conditions for AST were met. What does that tell me? So now I can say that the sum n equals 1 to infinity of the alternating series, -1 to the n, over the square root of n squared plus 1 plus n converges by AST. So to answer the question that was posed, what can I say about this original series? It converges conditionally. Very good. Okay, how was that? Tricky, I know. Okay, you'll get the hang of it. It's really following through the logic, right, of what the question's asking and your approach. Okay, let's do some more. I'll talk you through it. Here we go. We have the sum n equals 1 to infinity, -1 to the n, times 3n to the 4th plus 6 over 8n to the 6th plus 9. So what should you always test for first? Test for absolute convergence. Good. Okay, so take the absolute value of an. All it's going to do is get rid of this alternating portion here, okay? So we're going to have 3n to the 4th plus 6 over 8n to the 6th plus 9. Ooh, again, this is giving me vibes of I should do limit comparison test with the p-series. But how do I pick the correct p-series? Just look at the highest power of n in the numerator and denominator. That's what's controlling how fast the terms are shrinking. You could say growing, shrinking, whatever. So I see n to the fourth in the numerator, n to the sixth in the denominator. That simplifies to 1 over n squared. So I'm going to compare it to the p-series, n equals 1 to infinity of 1 over n squared. What does this series do? Well, since p is 2, which is greater than 1, it converges. Make sure you list all of this out. This is part of your justification when you do limit comparison test, that you can conclude that you know what your series does, okay? So here we go. Look at that limit comparison test coming in as our savior twice. So here we go. Limit n goes to infinity, 3n to the fourth plus 6 over 8n to the sixth plus 9 divided by 1 over n squared. So then this is limit n goes to infinity. This is going to flip up to the numerator. I'll distribute it through if you'll allow me. This will be 3n to the sixth plus 6n squared over 8n to the sixth plus 9. Again, we have an indeterminate form, infinity over infinity. I really save L'Hopital's rule when I have no other option, because you have to change everything to be a function of x. And it's like, we don't want the hassle. We just want to get this done. So the rule of thumb is divide by the highest power of n from the denominator when you have this indeterminate form, infinity over infinity. So let me divide everybody by n to the sixth. So let's see here. What do we have? Limit n goes to infinity, 3 plus 6 over n to the fourth, yes? Over 8 plus 9 over n to the sixth. Okay, this goes to 0, this goes to 0, and I'm left with 3/8. What do I care about 3/8? Only two things, that it's finite and non-zero. Perfect. So what does this tell me? Limit comparison tells me now that my series, the sum of absolute value of an, does the same thing as the one that I compared it to, this p-series. Well, I compared it to a convergent p-series. Therefore, what can I say? The sum, n equals 1 to infinity, of 3n to the fourth plus 6 over 8n to the sixth plus 9 also converges by, I'm going to abbreviate, guys, limit comparison test, okay? Good. They behave the same. Notice in the previous example that I did, will you allow me to scroll up? Okay, when we did limit comparison test for that first problem, we got a different conclusion. We got that our series diverged. Why was that? Because I compared it with the divergent harmonic series. So limit comparison test, when you get a conclusion, right, when your limit's finite and non-zero, it tells you your series does the same thing as the one you compared it to. They behave the same. I've been saying they're twinsies lately, okay? All right, cool. Now, do I have to do more work? No, because the absolute value of my series converged. Did you see that? That's the same as finding out, hey, this applicant has a 4.0. So do I need to go back and check? Oh, I wonder if they got an A in their most recent math class? No. Do I need to go back and use AST to check if the series converges conditionally? No, I'm done. I just tell the people that means the sum, n equals 1 to infinity, negative 1 to the n, 3n to the fourth plus 6, over 8n to the sixth plus 9. What can I say about it? It converges absolutely. You're like, hey, everybody, this student has a 4.0. So notice, I found out that the absolute value of an converged, which means that the original, which was an alternating series, converged absolutely. Okay. A little bit better. Okay. I have more. Don't worry. Now let's look here. We have the sum, n equals 1 to infinity, negative 1 to the n, times the natural log of 9n plus 2 over 8n plus 1. Now, I told you earlier in the video when we were looking at the flowchart, on occasion, you can just bypass the whole process and jump straight to Do you remember what I said? Test for divergence. If you can tell, it's going to fail test for divergence. It's like you get this applicant and you can already tell it's a 1.0. You're like, then there's no way they got an A in their last math class. I mean, I'd be shocked. So this is an application we're going to throw in the garbage, sadly. How do I already know it's going to fail test for divergence? Well, I'm ignoring this portion here. And I know this is going to approach natural log of, I can just kind of take the ratio of the leading coefficients here, natural log of 9/8, which is not 0. So I'm just going to jump straight to test for divergence and be complete with the problem. I don't have to go through any other steps. If you didn't notice, then when you test for absolute convergence, you'll get that it fails test for divergence, and then you'll notice it. So that's enough. Okay, so here we go. What's the best way to approach it? I would just say, let's consider the limit as n goes to infinity of, let me just leave the alternating part out because it's going to complicate things. Natural log of 9n plus 2 over 8n plus 1. I'm going to do this really properly, no pre-calc shortcuts, okay, in case your professor's a stickler like I am. So this is the limit. N goes to infinity. Now you can actually pass the limit inside to the argument because natural log is continuous on its domain. So basically what's going on is we have natural log of, like this, limit n goes to infinity, 9n plus 2 over 8n plus 1. You probably do that in your head without needing to write it, but oh well. Then I'm going to multiply everybody by 1 over n. Yes. So then I have natural log of the limit as n goes to infinity, get with it, okay, of 9 plus 2 over n over 8 plus 1 over n. Okay, so these go to 0, and then I'm just left with natural log of 9/8, which is not 0. And since I didn't include the alternating term, what's happening is that the odd terms and the even terms have different limits. In fact, let's summarize for the people. The even terms will approach positive natural log of 9/8, and the odd terms, they will approach negative natural log of 9/8, because if this n is an odd number, you'll have -1 to an odd power, so that would make all of these odd terms approaching the negative of natural log of 9/8. So what does that mean? If the even terms and the odd terms have different limits, that means the original, the limit as n goes to infinity of the alternating one, of ln 9n plus 2 over 8n plus 1, it does not exist, and therefore it doesn't equal 0. So then that tells me that the sum, n equals 1 to infinity, -1 to the n, ln 9n plus 2 over 8n plus 1 diverges by the test for divergence. Okay? And like I said, it's no big deal if you don't spot it right away. You're just going to end up doing more work that you didn't need to do, but it is what it is. Okay. I've got one more. Remember, I told you there were 2 tests that were all or nothing. We love them. Ratio and root test. As soon as I see factorials, I'm like, oh, we're going in for ratio test. And I love it. It's my favorite test. Okay, let's tell the people that's what's happening. Ratio test. So we're going to have the limit as n goes to infinity of the absolute value of an plus 1 over an. So this will be -1 to the n plus 1 factorial squared. Don't be scared. 8 to the n plus 1 over 2 times n plus 1 plus 1 factorial. Please make sure you put parentheses here. Let me put the watch out eyeballs so you don't forget. And then divided by the original. So I'm just going to multiply by the reciprocal. So I'll have 2n plus 1 factorial, and then in the other side, -1 to the n factorial squared, 8 to the n. Are we good? Okay, Now, when I take the absolute value of these alternating terms, they just become positive ones. So they go bye-bye. And then nothing else is going to be negative because n's going to infinity. N starts at 1. So I don't need to keep the absolute value bars anymore. So I'm just going to write this as limit n goes to infinity. Now, don't freak out about this n plus 1 factorial squared. Just think it's n plus 1 factorial times n plus 1 factorial, okay? 8 to the n plus 1, that's 8 to the n times 8 to the first. What about this 2n plus 1 factorial? 2n plus 3 factorial, guys. Oh, yeah. Okay, then times, we've got 2n plus 1 factorial. And then down here, n factorial, 8 to the n. How are we doing? Okay, we can do some cancellation. 8 to the n, get out of here. And then we need to break down the larger factorial so we can cancel with the smaller ones. Always break down the larger ones. So we've got limit, n goes to infinity. This n plus 1 factorial, I'm going to break it down. N plus 1 times n factorial. That's this one. Then I do it again for the other one. Once more, folks. You could write a squared if you're feeling bold. My students just usually are too nervous. So we're just writing it all out. It's okay. Times 8 to the first. Break down 2n plus 3 factorial. So it's 2n plus 3 times 2n plus 2. Stop here. Times 2n plus 1 factorial. Because I see the 2n plus 1 factorial on the other side there. And then n factorial, n factorial. Ready? It's cancel party time. I love it. N factorial, n factorial. Gone. Gone. Woohoo. What a party it was indeed. Okay, so then we've got limit n goes to infinity. Who's left? 8 n plus 1 squared over. Ooh, you see how we have 2n plus 3, 2n plus 2? You guys, I can take a 2 out of here and it's n plus 1. And then I have 2n plus 3, don't I? The cancel party's not over. Boom. Ooh, 8 and 2. Now this is a 4. Just so satisfying. Am I the only one having this much fun? I think so. Okay. Limit n goes to infinity. 4 times n plus 1 over 2n plus 3. Okay, infinity over infinity. So I'm just going to divide by n, divide by n. No pre-calc shortcuts for calc students. Limit n goes to infinity. This would be 4 times 1 plus 1 over n over 2 plus 3 over n. Okay, then n goes to infinity. This goes to 0. This goes to 0. I just have 4 over 2, which is 2. So what do I care about 2? I just did the ratio test, and I always compare the limit to the number 1. So if it's greater than 1, then that tells me what? It tells me my series diverges. Very good. Let me rewrite it. It was negative 1 to the n factorial squared times 8 to the n over 2n plus 1 factorial. This guy diverges by ratio test. And we're done. We don't have to do AST to check for conditional convergence. It's a no. Ratio test, root test, all or nothing. They either converge absolutely or they diverge. I love it. Don't you love it? Psh, yeah. Okay, so that concludes the video. I hope it was helpful. I actually have so many videos on sequences and series. I'll link the playlist in the description and at the end of this video. If it's something you need more help with, check out more of my lectures, and I will be back with, actually, I'm going to make a Calc 3 video right now. So whatever math class you're in, I probably have video lectures for it. Don't forget to give the video a thumbs up, subscribe if you haven't already, and follow me on Instagram and TikTok, Math with Professor V. Bye, guys.